No, it's not working. Yes. Okay. So let's get started. So I guess we should quickly review what we have been doing for lecture 5 because I know you guys are super busy. I mean, it's necessary to have a very short review. At least you know what we've been doing, because today we do a little bit different. I mean, but still based on what we have been doing. So lesson 5 in the last week, what we cover is generalizing regression results and also multiple linear regression. Right, the generalizing the results involve we in the lesson 4 we do a regression, the simple regression, and do different functional form. And the chapter 9 is going to talk about how you do confidence interval and hypothesis testing, and also for the model, right? I mean, just the main thing to remind you is how you would deal with this, and I would expect you know how to do that, right? I mean, probably expect you, if I give you this table, you should be able to tell me whether coefficients are significant, right? What are the p-values, what are the confidence interval by reading from this table, right? And then what are R squared? These are the thing that I would expect you to answer, right? I'm not, probably I will not be asking you to produce this, because some of you may do R, some of you may do Stata, some of you do E-views, many software. So I just include the software, but I'm not expecting to ask you this, but rather ask you how to read this one. Okay. To make our exam easy, so that's why I focus on the Python output. But if you use our output to be same, or Stata output will be very similar anyway. I mean, I think Python is more element there, but the same thing. Okay. So you do have a fast testing. I'm not going to repeat because I guess shouldn't be an issue, right? But anyway, I just do that. So this will be the coefficient, right? This is an error, and this is Z value, and this is so big, so actually they're no different from 0 anyway, right? And this is the number, right? It's basically mean 0 there, right? So there's nothing you can do here. And constant, and still p's bigger than 5%, so we can't really reject that. Okay, so that would be something I would be expecting to do. And then okay, R square, you can say R square is what? 0. So essentially, it means nothing this model is useful in explaining, because the data generated is a random, I write down random thing here. So you can see this Y is symmetric, right? X is increasing, right? So basically, X is useless, right, in terms of that. Then one thing probably I mentioned is the what kind of slope you would be using, and this is usually the formula you learn in the basic statistics class, and what usually people expect you to do is a robustness error, which is, of course, the formula is very complicated. I say required matrix algebra, which I'm not going to show you, but you can easily implement this using the XC3. This is very similar when you do R. If you do Stata, it's just called comma robust. Okay, so that would be something, nothing deep here, but you would know their formula, and you look at the book and a lot of application, we will have the robust version if we're doing this. And just to remind you, what is heteroscedasticity, or simple one, is whether the variance is changing according to X. If you make assumption that at different level X, right, the same, then you can use the simple one. Okay. But otherwise, you use this guy, right? Use this function. And there's also another prediction you have the model, you draw a line there, right? And the line, do remember that the line simply means just the average value, right? It's average value. It doesn't include the error term epsilon. So the simple version is much easier, right? But when you look at the one for the average value, you have one more here. Why one more here? It's just because of you have an error term. You look about individual value, not the overall value. Okay. So I guess it's easy to see how you can construct this from the Python. Okay. So I'm not going to that as well. And the multiple regression is the most general format that you learn for the regression model. And essentially said, I'm trying to explain the variation of y by a bunch of random variables. And the way to do it the same as simple regression and minimize the vertical distance, right? And actually in terms of two variable, right? Basically, if in a plane, right? There's x1, x2, this is y. You can have a many point there. You try to fit a plane there, right? Not a regression line, but rather a regression plane. Okay, it's a plane. Okay, the plane is trying to minimize the distance of the point in the three-dimensional space. Of course, it's hard to imagine how you do it more than two regressors, right? With x up to xk, but in mathematics, there's no different. Just do in the hyperplane, they call hyperplane, right? Just say, imagine there's a plane there, but I don't think our human mind can handle more than two, but the idea is the same. I mean, because now you can disentangle the geometric meaning, just algebraic stuff, okay? And from then, we learn how to do the coefficient. You can see the matrix algebra go to here, but we are not going to need to learn this one. Instead, we'll just rely on the software to give us the same stuff. Okay, we just OLS formula do the regression. Okay, so this non-robust, right? But still, the interpretation is the same. Look at the p-value, whether p-value is less than 5%. If so, then you're done. Okay. One additional thing is you sometimes want to see if both of them are zero, right? Is there any, because look at this, is looking at every coefficient separately, right? You want to test how usefulness is the whole model. And you look at the F, look at this two number, okay? Probably, I'm not sure if I mentioned this, but if you want to look at this, this is the F statistics, okay? And this is testing simultaneously whether x1, x2 will be a useful model. You are comparing this model to the baseline model that y is equal to y bar, right? The basic model, right? It's like you never use any x, right? You just, the best model is the mean of y as a prediction of y, right? And you compare that model with this model. I'm not going to give you detail, but how we check this is called the F test. Look at this guy. This guy less than 5%, your model is fine. If your thing is not more than 5%, not less than 5%, even itself is less than 5%, is usually not fine. So your multiple regression, you have one more thing to check. Usually that's not an issue, but I need to mention that to you as well, because when you have a whole lot of data, usually it's not a big problem, right? Because we mentioned that when you're big data, usually for this P will be very small, and same as the F, it's going to the p-value will be very small anyway. But we have to say it out, right? Because this is the standard way to do the testing. Okay. And this is the thing. I mean, if you learn undergraduate, you learn statistics, that is something that nothing new there. And Also, there's something you call log likelihood, AIC and BIC. We'll probably talk about some log likelihood today, some of them, and the AIC, BIC, we'll talk about this 2 weeks later. So, and for regression, they're not very useful. For regression, is R-square method. R-square is how fit is the model. Okay, and later you will learn today, probably today we learn likelihood. Then later you will see that this likelihood, we want it to be as big as possible. That is we're trying to do. AIC and BIC is what some information criteria, and they will be useful when we talk about prediction later. These are the model. These are the measure that is like R-square, but R-square is only useful when you compare the same type of regression, right? And it's usually not about selecting a model, but just telling you R-square is telling you how it fit, right? And by definition, if you add more variable, R-square will increase for sure, right? Because you add from x1 to x2, the worst case is you don't use any x2, right? X2 is 0, the coefficient, right? So R-square will always increase, right? So that's why you would use the adjust R-square if you really want to compare different regression model. Okay, look at it. Adjust R-square. It's similar to R-square, but adjust to depend on number of coefficient. So it's just divided by n minus k minus 1. But it's very similar to R-square, but just some constant different, depending on how many regressors you're using. So when you talk about multiple regression, you compare model A, model B, model C, or a linear regression, and then use R-square, adjust R-square. Okay, so I think this is you learn undergrad anyway, just to remind you again. So just to reiterate what I have said, okay? So I'm not sure I mentioned last time. F-test and the public F would be looking at, you look at this coefficient at the same time, whether they equal 0 or not. First thing. Second, when you look at regression, okay, you want multiple regression. You don't really just want to look R-square. R-square by itself is still explaining how much variation you're doing. That's no problem. But when you try to compare, say, a regression with x1, x2, and the regression with just x1, or regression of x2, then usually you would use adjust R-square rather than R-square. Okay, so that is the way you want to select different model. We will talk about this later, not now, but sometimes we are being lazy. R-square will be similar anyway. You look at machine learning, they just use R-square as well. I mean, sometimes R-square. I mean, I think for regression, you adjust R-square is better. Later we will see when we do prediction, we will see machine learning, and then we'll do R-square. Okay. But not the moment. And these two, when we talk about machine learning, then you will see these are the method that we'll be using. So don't worry about that. These things will be used. Actually, you will learn most of the stuff in this diagram. Because when we do, today we'll do the logic and profit, we will also see the same thing. So don't worry about that. Probably I didn't mention is because we didn't do that. And you can see this is stargazer. This is kind of a production table. And you notice in this regression, the R-square is positive, right? Adjust R-square negative. It's possible because adjust R-square is not guaranteed to be between 0 and 1. So the interpretation is a little bit different from R-square, but still you want to be bigger as possible. Okay. And in that case, then it means that this is better than this guy, right? This is right, but okay. And last time I also mentioned if multiple regression, you have a variable that quantitative one, right? Instead of continuous, you can still run regression, right? And this is actually, if you learn ANOVA, analyze of variance, this is exactly what's going on there. Because if you remember, I mean, I don't know anyone study analyze of variance, that is a comparing mean of different groups, right? And this is the same goes on here. Anyone learn ANOVA? No, that's fine. I mean, you don't have to. But for people who do undergrad in search case, they should know, because ANOVA is something we cover in the introductory class, and you can look at the if you want to know the ANOVA more, but it's not important for our class anyway. But the undergrad stat notes tell you how to do ANOVA. These slides tell you the analyze of variance, and this technique actually is regression, but it's before regression appears, and it's very useful for people doing experiment and this kind of stuff, right? Because the idea is you have like male or female and look at comparing the mean between female and male. Then you can say that is there any wage difference, right? And this is one way, and then you can also have a two-way ANOVA, right? You can look at the consumer different by gender, by age group. Do they different, right? So different of the consumption amount in your store is driven by the gender or driven by the age, or in particularly some gender group and age group will happen. But I mean, you can do regression for this one. So that's why we didn't, the modern statistic, we don't directly go to ANOVA, but ANOVA is the way that actually people come do it before the regression. And you go to medical school or another quantitative social science, they often the time do ANOVA, right? Because grouping is very common. But you can just simply run regression like this. Is actually an ANOVA model indeed. One thing ANOVA compared to we do standard regression is ANOVA explicitly assume the error term is normal. That's how you do things. But when you have large sample, there's no problem, right? So the same thing happened here. But anyway, and you can do different type of interaction depending on how you think that the dummies have a different thing, right? Suppose you have a thing that age and gender, in this case, right? The gender and age would have different combination effect, then you just interact those. And probably you ask, when you do regression, what kind of stuff you should add, right? Usually what the standard practice is you try to add as many variables as relevant as you think. Okay, it's a bottom-up approach. Usually you put every single coefficient there. Okay, and then after that you try to see dropping those will change the result. Okay, or sometimes you do a top-down approach. You do a univariate regression, like you do 1 and 2 first, and then you try to put the whole thing and see how things changes. So it depends on the data, but usually when I learn statistics, that the teacher tell me you have to estimate the biggest model you can estimate first, and you check the t-stat and see the p-value is less than 5% or not, then you try to see whether you drop those. But unless, I mean, probably you learn at the end of this class, at the lesson 10, you will see, you will just control the thing that is relevant. Okay, we will talk about this at the lesson 9, 8, 9, or 10, 8, 9, and 10, then we will learn what kind of variable we put here. And up to now, we just give you the regression. Later, you have to decide what is appropriate thing to put there. Okay, it's not something that you try to put whatever thing is here. Okay, you only put the thing that is relevant for our question. Okay, and what should be put there, it depends on the question you're asking. It's not mechanically, okay, this is related, you put everything there. Okay, you have to depend on what's the investigation, what's the question you're looking at. Okay, but you'll be very clear when we talk about at the end of this course. So I'm not super worried about that part. I guess I end here somehow, right? Last time. So probably I didn't talk about this y hat y plot. Okay. This y hat y plot is indeed one of the very useful thing that looking at how good is your fit. Did I explain why? I didn't. So y hat y plot is the following. It's a scatter plot. Where, as you can see, I didn't do it the best. This is 45-degree line. This is 3, 4, 5. Before, I mean, I should include 0, but anyway. But you know this 45-degree line. What does that mean? If your model is perfect, okay, it's nice, then your all the points should on the scatter plot, right? Because this is what you observe, right? This is what you predict, right? And why this is important, of course, this tell you how to do the prediction. I don't think I need to go to the Python because it's very simple, right? Because just for each x value I have predict, I have the y, so the same, right? Because every entry I have x and y. Maybe I talk about that in case you confuse how to plot this. This is a scatter plot, right? And when you estimate the model, you have this guy, right? And every data x1, y1, right? And x2, y2, so on and so forth, right? But for each x, you can plug in the model, you got a y hat, right? So you can just plot a scatter plot based on this guy, right? So that's for each x. I mean, of course, you have a bunch of x is a vector, right? X is a list of number. But in here, you have a estimated one, and you flip again this two, okay? And why this is important, right? Because you look at the horizontal distance is important. Let me convince you why horizontal is important, why you plot it this way. Look at the example of the hotel. Okay. And in your model, your prediction is a line, right? Actual observed is this guy, right? So the lowest the distance, the higher the distance between the line and your point represent the biggest bargain you have, right? Because according to the model for some x, the price will be there, and you observe this is your price, right? If you want to find a big bargain, this is the way you look at. Is that clear? Is that clear why this is the case? Let me repeat. How you get this point on this point, right? This is this y, right? Coming from what? This y is coming from some x, right? So I suppose this is the case, right? This is the case. Let me talk about that, right? So this number, right, can come from some x, bunch of x, right? Xk and then y, right? This observation, right? For some, you control some location, the star, whatever, you control it, right? And the y is here, okay? I just control the y is the horizontal location, okay? And but you based on what you can control the x, you can come up with y hat, right? Which is this location, right? It's here, okay? And based on your model, it should be here, okay? But what actually got is much lower, okay? So so this is a good bargain, okay? So that's how we look at bargain. But of course, if you don't want to care about it, you simply can say the closer this to the line, the better the regression is, okay? And that is how we look at regression. But we don't go into detail of those. But this is you want to see how good your regression is, and we'll talk about the measurement. Probably today we'll talk about y. Look at distance. Okay, one of the measure of how good the regression is look at the distance of this one and square. Sum of the square distance of this is called the Bureau score. Later, I think we got to talk about today how to measure that. But let me end here. I guess that shouldn't be a big issue. So now, I guess we have enough review. I hope you would be okay if I extend our regression here. Okay. So for the class of today, we'll talk about actually a more complicated data set. For the first one, it's called the modern probability. So what effectively is Y is no longer a continuous random variable, rather a binary data, 0 or 1. Why we have that? Because sometimes I want to explain how many people would buy our product, yes or no, right? Only predict that. It's not taking account into how much amount he wants to spend, right? Or did the customer actually buy the VIP package, or whether they go to the business class or economy class, right? If an airline, right? Or do they, as an IT manager, whether they click the button, right? They click the like button or not, right? That is something you care, right? It's whether they do it or not is binary, and we want to do that. And you will say, okay, can we do regression? Yes, we can do regression, but later you will see there's some problem with just putting regression there. So that's why we learn a little bit more advanced. We learn probit and logic. Of course, there are many other ways, but we focus on the simplest one. Okay. And the next one is called time series analysis. Okay. And one of the problem that when we run regression, we have assumption, which we didn't say explicitly, is each observation is kind of independent, right? What you observe, I have an observation on one person and on the other one, right? But time series is like I have a observation of a single person over time, right? That means that probably I have the guy who would be looking at his consumption in the website over the past week or months. The problem of looking at this kind of data is how much he's spending on your website today and tomorrow is not independent, right? If he is rich or he or she is rich, he'll tend to spend more, right? Because, or the case is like if he already buys something today, he's not going to buy tomorrow, right? Because no longer he's not going to spend all the time. So that's a what we call correlation, right? What we call serial correlation indeed, right? Called serial correlation. And we need to use some technique to handle it, okay? And we don't cover much. We just scratch the surface. We don't even talk about ARMA model. I mean, if you know what ARMA model is, the auto-regressive moving average model. We just touch the surface a little bit how to do that. If you do want to do more, then we'll be beyond the scope of the class. But it's already in textbook as well, if you want to look at those. And I mean, these two topics, if you go to the undergrad or even the stats department, they will spend whole semester to cover even. So we just only cover in 1 hour. So you can expect how much we can cover. So, but at least we give them idea how we do things. And probably it's important because when you do machine learning, although we don't have time to cover that, one thing is important is called classification method. For those who will learn machine learning in the elective class, then you will learn much more. There's a lot of what we call the a lot of method, nearest neighborhood or whatever. But we are not going to talk about those. But anyway, let's model those, okay, quickly, okay? And don't worry, you look at the regression with the same format. We just change the OLS to probit in the Python code. So the Python code is absolutely easy. There's nothing new there. And just for the math, it's also very easy because just change the way how we fit the model. It's not about minimizing the vertical distance. We'll talk about how we get the coefficient. But very quickly, it's called maximum likelihood. But before we do that, let's quickly start with this one. It's not complicated, but just we need a new way to handle the data, okay? And binary data, yes or no, 0 or 1 is very important, as I mentioned already, because sometimes you just care whether they buy the stuff. right? Whether they become a member, premium membership, okay? And how to model that? Here we would focus on, instead of talking about 0 or 1, we assume that we are modeling probability by itself, okay? We are trying to say we are not thinking this is 1 or 0. Underlying, we are saying is a probability, okay? Although the data you observe is 0 or 1, but you assume the underlying thing is from 0 to 1 instead of 0 or 1. Okay, let me say it again. Okay, the data you have is either 0 or 1, but you are going to model it as the data actually goes from 0 to 1. Okay, that means your prediction is not 0 or 1. It's a probability. It's a number between 0 to 1, right? It's a probability. Okay, if you want to actually tell you that it's either 0 or 1 as a result, that is the machine learning called classification problem, which we don't cover because other section design on the cover, so I'm not going to cover, but you can check the textbook. They talk about classification issues. But we are focusing on the case where we just measure probability, okay? So if what we call the LPM is called the linear probability model, LPM. So just basically, as I said, you just run the regression, right? I mean, there's no restriction on how the Y should be, right? I didn't say Y have to be continuous, right? We can still say, even Y 0 or 1, right? Yes is yes, yes is 1, 0 is no. You can still run the regression. There's no problem, okay? And it's easy, okay? And you just run it, okay? So let's look at the application, right? Here, this is a very common problem, is people want to look at whether smoking is going to make you less healthy or not, right? Of course, I guess now everyone knows it, but you have to prove it, right? It's not clear there's a proof there, right? Similarly, people think, well, drinking is going to healthy or not, going to reduce your health, because some people said drinking, I mean drink alcohol, right? Drink alcohol make you happy, right? Happy people live longer. So we don't know. No, don't laugh. This is actually actual research, okay? And not I make up. Actually, the actual research, people doing that. You know, drinking is for sure is damaging your physical health, right? But drinking also improves your mental health, right? And it's add and subtract, right? I mean, physical health is weaker, but mental health indirectly make you live longer, right? Sad people die earlier. I mean, that's a well-known fact, right? And so, which effect? I mean, you have to look at regression, right? Here is look at this and look at whether they live healthier. Okay. So they do is look at people pretty old, 50, 60, and look at them, they're healthy or not, ask them for a year later and after they smoke and see how the data looks like. Okay. And 1 is healthy, 0 is not healthy. And the data comes from Europe. I think Europe is good because Europe has many different races, right? And then different demography and geography is very different. So they look at the data. But of course, the data you can look at, they just self-report. So how well you think is valid, I don't know. I mean, if you look at their health report, then it more makes sense. But you can see, but they just try to illustrate that anyway. Say they run the most simple one, as you can see, right? Look at linear model, look at the smoke, whether smoke and healthy, right? Remember the healthy is a CO1. Smoke is also CO1, right? You smoke or not smoke, right? So they look at coefficient, right? Is 0.072. What does that mean? It means that if you change from non-smoker to smoker, that 7% of people, 7% less people report they're healthy, right? So suppose 100 people report they're healthy. For the case of non-smoker, you have 93 people saying they are healthy for the smoker. Is that clear? Let me repeat, okay? Suppose you have 100 people, suppose make it simple. Suppose you have same number of smoker and non-smoker, right? And then you have 100 people reporting they're healthy for those who don't smoke. Then look at the smoker, you have 93 people. Okay, is that clear? Okay, so the percentage is less. Okay, so something like that. Okay, this is the non-smoker, right? This is the size of the dot represent 100 people, right? And this they are healthy, they're not healthy, right? And this is healthy. Of course, this is higher than this one, right? You can also compare, but looks like this, right? So this is the slope, right? So on average, let's say 7% more people, right? So as I said, 7% more likely, right? So you smoke, that means that you're 77% less likely you would report you're healthy. Okay, after 4 years of smoking. Okay, so of course, and they said this is a linear regression, just one variable. Then you probably want to have a multiple regression, right? Control the age, control your health status, and so on and so forth, right? And take the functional form. So here you can see the example is education, okay? And very interesting is non-monotone, okay? You will see the healthy is like this, S shape, okay? And income is like this shape, okay? I think it's good time to have a break. You have think about why there's an S shape. Think about that. I guess I give two little question for you to think in the break. So let's think about the reason why you would see that. Okay, I think it's a good exercise for your mental. Hopefully you don't check out the solution at the later. Okay, it's good there's no solution. So think about why this would make sense. Okay, so let's a break of 15 minutes and I open the U reply. You can discuss with your friend why that's the case. And in the meantime, please fill in your group in the if possible.别的课用这个吗？啊？用这个吗？所以我会是唯一的调这个东西。教这么好的，我发现调这个小卡，这个让大家不要无聊。哦，对对对，这个哎好啊，连贯。
Right? Yes, this one. And so you have many data there. And the size will not represent how many of them. So when you both have data, there are many data, right? The bigger the bigger amount. So that's why I can do. Very much. P-value cycle 整理係嘛？個 M 係呢個大換，呢個就有零有零就死啦。係啦，有正有負就得啦。點解呢個有係啊？呢個應該 out 係啊？呢個係 beta 1 beta 2係三個啊嘛，我哋咁兩個。因为 T 已经跟银行贝尔贝塔问题，那个我的贝塔都是咁 R 就係睇同一個 model， 即係就睇佢有冇用。如果你要 compare 就一定要 R 係 just R。
Right。有你的 F 開始寫的東西 ，X 零就是。 at least
数字有没有什么？
我们 F 看那个0.05就好了，一样。
就是也是看 P 值嘛。
啊，对，看 P 值。
但是我没有 P 值，我只看 F 的话，是大于多少？哎呀，不一样。
但是 F 是两个东西嘛，对吗？有，对啊，你不要我讲了吧？你可以看笔记，书都没有讲，为什么有讲？啊，可以的，就是 SSR。
哎呀，那看都看不出来。
对啊，对啊，看比较好嘛，你放可以的。
0.0吗？
对啊。
0.05，至少0.05还是 OK 了。0.05就个人。
我的会记这个东西，我不用到公司就上了。我大部分就是不用到也有用的东西。
他们联合起来，就是我看 F 是他非常有一个他
这种工作。
X 3我觉得都有用。
对。
然后就有情况说，我 X 以后还在全开，然后只有 X 它是。
所以首先你先用 F 来检测 F 减 B， 用 F 减 B 证明那种回归比较以后再看。可以连带，不一定连带是可以连带。不一定连带这个是统计的一个是很复杂的 ，model 在很低的，高数有的像我说的话，我不能接受你说的这个骗你的。你可以连干，但是这个不是要很复杂的问题。我们今天会讲到这个，以后会讲的，因为怎么整的这种模型的话，有两个问题，是做 prediction， 那很简单，有很多 AIC 啊、R 啊这些。但如果你说 interpretation 的话，那就另外一讨论就是工作能力比较对对。我的 model 叫做，对，所以有问我的问题了，就详细的分享。
还有那个 adjust 对啊 adjust R square， 它那个地方你刚才有讲说
square。
镜头啊，R 还拿差的，它就是
R square 跟那个 R square 主要的叠加一 adjust for adjust for number of rate， 所以你可以比较不同的 regression， 可以看到how
对，就那个 adjust。那我什么时候看
？After 高度，那个 model 都看，
对啊。
But it's not proven。我跟你说，就是说，有一个 model 一个 R-square 是0.8，另外一个 model 是2个东西叫0.9。对啊，但是你怎么 compare 就很难 compare。R-square 没有0.9，因为它可能多一个变量肯定是更大。哎呀，但是你哪一个比较好？我看还是 R-square。
我跟全看起来是。
就是R square 是我。
Just for number of variables。
比如说我这里有5个，因为它解释的，它有个 X， 然后那里有6个，解释的，
可以用 adjust R-square。
就是它是不会也被它的增加。
这会小数。对，这是明显的 adjust for。You will compare two different regression, linear regression, then just adjust R-square is better than R-square. But I'm not saying that is the best way you will do it.
就是这张一类的不要，一个类
你 compare across different model。
变量的时候，adjust R square 和是然后有6个，
会下降对不对？啊，有下降。
没有。
对。R-square 因为可能可以用 R-square 怎么讲？说譬如说两个。
对。
可能
但你的那
个很大的数目，你哪一找一个好回归 compare， 比如说你的习惯 annual， 还有习惯，比如说今年的 data， 你考前一年的 data， 跟后年的 data， 你看 R-square 变化可以说，你可以用 R-square， 比如说同一个回归嘛，不同的习惯你可以说，在 model small fit。对，然后可以用，但是不同的 regression 的话，你看很多 regression 也可以 R-square。
对，这个是例子，
每次都一样，对。
就我想知道他俩例子的交替，因为这是大家的例子。
对。
就 就是他说的，
简单的说，有200个抽烟的人，有100个抽烟的人，他还对，因为的就是你的有100个抽烟的人，还有多少他人的都到这个，到了，就是说，以后来抽烟，还是那种到美国对吧？他要就是以后抽烟的话，下来把一系列就会有less 没有说过多没有说我也不知道 on average 如果你抽烟的话，你要7%的risk
他是说，其实他没有要求，对吧？因为所以就不知道说你知道他要啥。
非常的，跟老师的现在他就想要3个，你这个增加的，
那我先我来
做完把这个
你说一个发明可以呢？他要2年大哥，
以前就比较适合那种，好像也有很好的，包括这个
希望他
这个
那他那就被很多买。
如果是一个方法，这个比较一个 P test 或者跟对不对？如果 model 通过很多
哦，
比如说你 compare， 比如说比如说用淘宝、用京东、用一个拼多多，对吗？他们的收入什么上不同？比如说 compare 京东跟淘宝的话，我就不太熟悉。
所以很多码那一个开始就
类似就是扩展。
那就像是ASP 那个大概是
R square 是在你要看跟 R square 跟多少个？但是 H R square 的变化可以解释不同的还有R square 是这个东西。
对啊，Looking at 这个
SST and this is R square is 分比嘛 ，OK， 这个是 R square， 所以它要多 fit 这个 model。如果是just R square， 基本上这个东西只要加点 adjustment。ANOVA 是说这个情况，你有。
ANOVA 同 hypothesis test 係咪有？即係佢係同一類型嘅嘛？
它 hypothesis test 裡面是 compare the variance， 所以最简单。JD
即係幾晒大佬
阿里巴巴拼多多什么？
拼多大家都懂。
PDD
Okay, PDD, right? Then look at the spending difference, right? Your data 10, 11, 12, 15, 16. Okay, something like that. You want to see whether the group mean are the same or not. 对对，看到的对对对，就是。RMSU 是 SSE 吗 ？SSE MSD 好，拿去。You want that? 大家注意这个分子，你看你跟那个 R 是吧？
有时候以前做那个用 R 跟它那个哪个不同模型好像都不能反映哪一个是用厂商给我下版的话，
不是我们会找咱们俩都接受
好，高三是不
有什么听题？你看太快了，太早。
不要放弃了。
真的，
都
在搞还有
啊？
要我们讲啊，会不会讲吗？我们讲完了就
考试稍微不考试走吧。
我就是拉里面有讲的，不然没讲就不用考。不久跟你说考了，我先读，
都很清楚在考什么，你们不会都没有办法。
不能每次都在这里喝。
有喝你啊，啊，考下来了。没喝这种，这种很土的东西。你现在讲3个小时讲不动了，很多会的东西。
我听得动啊，
你们听不动我也讲不动了。下期大家挤，大家挤关过来，大家答问题，答对问题就可以了。我办公室很多，各种各样的。
多打一点。
好，都来，各种各样的，可以。这个切 ，That is what you want。
又可以节省点学费。这个课程下次课程。
你的朋友应该就是那个3天的都，
主要是同学都有扣水，
对，
学费很贵啊。
是啊，所以我说你再薅一点奶茶吗？
可以，
你看老师很不错。
对啊，我在弄点啥？你不到，
呢個借校分數，即係高分都即係 stand up 對，
我怎麼搞？哎，我不知啊。我搞到我搞到現在。
你即係 keep 住
我有啲佢識我啲，
即係佢叫你搞。
佢教你我識上大家溝人，教大家溝唔翻佢，我嗰兩日咁啊，咁費事嘅啫，我哋。common core 啊，
就是在攞啲學嘅。
好啦，我就教嗰啲教我教嘅嘢就係冇所謂嘅，或者有用嘅。
有用。
覺得我教嘅東西對 minimum useful knowledge that is sufficient for the purpose that you actually do. 看，你知道现在那个 Netflix 那个 CPU 为什么多一点？有分析这个东西啊， 那个 CEO 你放了3句话的回归下，他要放哪些片啊？你特别喜欢什么？你每天那个看那 Google 啊、亚马逊啊、或者 AI 啊、淘宝啊、TikTok 的话，为什么你扫出来？你扫出来小红书，扫出来他们没办法呀，后面的话。对啊，这比白一点而已。你看它底层的逻辑是一样的，但是我们当然不会教这么复杂，但是利用就平常。那个内核平常很简单的，就是很基础的东西，其实对吧？你想看到就它比较它 data 别人多，都是很准。对，其实没有很难的东西。
So let's continue. See how well you're doing. What the exercise to recommend? Running, I guess. What do you mean? Exercise mean textbook exercise? Recommend. I guess it's you can try the exercise. Well, the problem of this, I mean, one of the classes, this class is like where we apply, and most of textbook assignment is very theory. So I'm not sure whether exercise actually help. And as long as you know what I have just said, right? Basically just like how to interpret those, then should be fine. And look at I think if the good is look at the case study actually in the book, that would be very helpful. I mean, because we are basically revolving around the knowledge about that point. And yeah, look how you understand the table output of Python. If you know that, then should be fine for this class, because that is what I'm asking, right? What those scatter plot in page 9 mean? I suppose page 9 means this one, right? What does that mean here? Look at the data you have is all the binary, right? You have each observation, each subjects, you have whether he's smoking or not. 0, 1. Determine whether you're here, right? And you also know that they are healthy or not, which is also 0, 1, right? Health is here, not here, right? So the scatter plot only have 4 different numbers. So then how to represent scatter plot is the size of the dot. Size of the dot. The bigger the dot, you have more data point here. So it means that there are very few people who are smoker actually stay healthy, the size of the plot. Right? Suppose this is 1 cm, this is 3 cm, means that there are 3 people here, 1 people here. Okay? Same goes on here, there. Okay? And then this actually you can do in Python. If you have time today, we'll talk about that. How to plot with, we'll do the C-bond package to determine the size, or I also can do it. Okay? But this is saying that how many people there. And of course, even you have 4 points here, you can run regression, right? Because there are dots here, but there are many dots, right? So you can still minimize the distance of here. You see, right? Because you have this distance multiplied by how many of them, right? Same distance multiplied by them, and so on and so forth. You try to draw a line to minimize that, and the negative 7% is come from here, the slope of that. Wait, question. Your question? Because looks like you are not very happy with my explanation. With the smirk in your face, I figure out that maybe there's something I didn't explain clearly, but wow. Happy weekend. Yes, smoking makes people healthy. Homework is hard, okay? As I want to emphasize, our class is very applied. So I want to give you the idea how research is being done, and if you actually ever apply statistics in your work, which probably you might do, and this is the standard thing you're seeing. Okay, and I hope you learn from that. I mean, rather than just assign you the assignment in a textbook, that will be not very useful, right? Because you spend the money, very expensive for this class, right? The cost, and you want to learn something real, then I just give you the project actually you're doing. I mean, of course, you also work on your own project, but you see, I assigned the assignment that is actually part of my own work, so you can see how I do my work, and then hopefully that will guide how you write your own project. Because rather than you proving this, and that is not very useful for a class, right? It's a master course, so hopefully that's good. Oh, someone give us a very important note. Probably they learned in undergrad is when you compare mean of two group, and then you probably want to check their normal, whether they equal variance. Yeah, that's it. But in our class, we don't go into detail. We just, okay, just compare by t-test and that's it. There are a lot of complication for each single thing we talk about in this today. But or the whole course, there's a lot of assumption we need to check in here and there. But the thing is, in general, no one check. So that's why we didn't teach. It's not because of they're not important, because those usually we don't really care that much. But of course, I mean, if you by formality, you should also check those, because you look at the textbook, every single thing you have bunch of tests you can do. Okay, but you don't do all the tests, right? So you do body check. You don't go to the hospital to do check one from A to Z, right? You don't do every day, right? But you just do some of them and then you work it go, right? So yeah, there are a lot of stuff. I mean, but we don't do it in our class. Okay, I mean you're very advanced, but we are just being easy. Okay, because there are many things you can do for sure. A bit tired, yeah. I think so. There's a time series model we'll talk about today. With the time is actually different day of the week is very different, right? Okay, everyone know is that's good. Multiple regression, yeah, that's good. I think everyone is following. Smoking, okay. What kind of thing you're smoking? This is just example, not the smoking. So I think we are right in the sense of master program is an undergrad. You should be feeling that there's something you don't understand for sure, something you understand a lot more. Because as a teacher, I can only cater for the median student. I mean, must be some of you will feel very easy, some of you feel very difficult. I mean, I do apologize for you think it's too easy. If it's too hard, then the best thing, talk to TA or me. I mean, try to help you. But otherwise, I can in the class I just can cater for that. Okay? That's why at the break you can ask me. Please feel free to do so. If you have substantial question, just send me an email. We will see how to solve the problem. I stay up 3 line to learn R. I'm so sleep. R, I'm not sure whether we're going to cover R. Depends on how things go. Maybe we can cover R. Or at least I may probably cover R from undergraduate class in the B.A. lab. So there'll be some extra spot that you can go to take. I mean, that I will let you know. You want to learn R. This is something I don't understand, but is it a joke or what? I thought there's some kind of food, right? Okay, not try. It's not healthy, right? Okay. I think everyone mentioned my haircut, but I don't think I sleep very well, so my hair goes up. Whoa. I like studying. I'm painful. Drinking lives longer. That's true. I said. I mean, there's a study in D looking at data in a Scandinavian country, Denmark. They figure out that actually drinking and moderate drinking actually ultimate effect is positive, because I mentioned the mental effect and the psychological, physical and psychological effect and physiological effect, the mental and the physical. And mental effect can better than that, right? Assignments look a bit hard. Yeah, I agree. I mean, but the assignment, I don't expect you to have fully correct to get the full credit, right? I'm expecting you try the thing and then try to look around, and this is the practice. I think as long as you do a reasonable attempt, then you should get most of the grade. Maybe I, of course, give some little bit more marks for people who do better, but otherwise, you don't need to too much worry about it as long as you attempt correctly. You should get, I think I write down 80% or 70% at least if you ever attempt to do that. So don't worry about that much. Okay, I hope that should be fine. So I don't know whether you would come up with the explanation to explain why education would look like this. Okay. So how many education you have? I don't know how many years you have right now. Do you notice how many years you have? Excluding your kindergarten. Of course. Kindergarten don't consider as education, I guess. How many years you have? You don't know how many years you have? That's so difficult. It's not asking your age. So you have 6 years of undergrad, primary school, 6 years of secondary school, right? 3 or 4 years college, and then 1 year right now, right? So 12 years is the standard. You go to the secondary school end, right? And this is what not keeping 24. I guess you also consider the 3 years of because in Europe, so I think they have a formal kindergarten. I think they also consider kindergarten here. So I think here is like this is the end of the secondary school, and this is bachelor degree, and this is somewhat like master degree and PhD. Okay, so you can see you guys are here, so you guys are pretty healthy. But if you do more, then probably not good. So here is fine. I mean, like me, like PhD, right? Not very good, right? So it's okay. But when you go down, it's like not very healthy. Now I think you understand why it's not so healthy. Yeah, probably if you are working in a physical demanding job, which usually tend to reduce your health, right? Look at in the animal world, what kind of animal live longest? 黄巴, right? So the tortoise not moving, right? So they live longest, right? And those other animal, I mean bees, they live long. So this is the outcome. So that explain, right? I hope, and you can explain why go down, right? Look at me. So it's easy. So look at income, okay? Also goes up. That's very natural. Okay. So I mean, why I want to bother you with this guy? Because when you try to have the data as nonlinear, you have to explain, right? Whether either it's a data issue or what, right? So I'm not trying to make fun, make joke or what, but this is something you have to explain. If you have a scatter plot, it's nonlinear. I mean, linear, not linear, but increasing, you don't have to say anything. If like this, I mean, your boss will ask you for sure, right? At least I will ask if I'm your boss. But so you can see this model, right? You will see if you are a smoker, actually you control everything else, become 6% less likely to be healthy, right? So which meant that you control other thing. Actually, the main thing here important is the education, right? And turn out that if you control education, actually it's okay. And you can imagine that because of some of the people who actually smoke are the people who are educated, because maybe probably have a lot of stress, but maybe because the income they're higher, they kind of compensate, right? And then look at the BMI and so, right? This is if you are much fitter, right? They stay less healthy. I don't know why negative, but turn out to be like that. Exercise regularly, okay, it's good. Okay, so it's interesting because if you smoke, you exercise, oh, that's fine. I mean, somewhat fine. I mean, but I'm not encouraging you smoke, okay? But that is a good outcome, right? Exercise is good. So I think CHK is good because you are a Hewley campus, so you are forced to exercise one way or the other. So you are much healthier than people who will go to other school. I mean, it's not surprising because I look at where I live when I was a kid. Is in a mountain, is somewhere here in the mountain. There's a housing. I always have to walk up. Okay, there's no bus to walk up. Okay, it's not a rich place. It's a poor area, so you have to walk up. And I compare to where I live is somewhere here. Okay, and no people walk. And I look at the elderly. Here the people at the elderly is, I think, how many floors? Yeah, I think 8 floors. 8 floors. I mean, go up 8 floors. Every day you go up 8 floors. Yeah, go home. And this one, I think it's just now I live like 2 floors. Okay, and look at the elderly, and people in this place, the elderly is very strong. No one use walking stick. Okay, here, many people use walking stick. So you can see, if you're forced to walk, that makes you healthy. Even you smoke. Okay. So I exercise is good. I mean, there's no doubt, right? Anyway, so you can see these coefficient and your confidence level. So, but the thing is, the interval is very wide. So probably is not saying that smoking might actually have no impact, but still is significant. Okay. So that is something you would try to interpret, right? So I guess I'll expect you how you can interpret this table. If I try to give you this, you can try to say, suppose I give you this kind of table, you should be able to tell me what are the importance, what conclusion you can draw from this table, right? You can draw, especially look at the stars, right? Look at this, and if they are this, you can say something, right? And then this what expect, because at the end of the day, this is the main thing you need, right? Who care about regression? How to do regression? Just plug in the Python and you get the result, right? Everyone knows how to do that. The important is how to interpret that, right? How to use them. Okay, because we are not statistician, right? At the end of the day, you are manager, right? I think your master course program is called IT management, right? So you're manager. So manager don't run regression, right? You read regression and do it, right? So at the end, this one is the LPM model is good, but there's one drawback here. But the one drawback is you want to predict, right? Look at the Y predict. The problem is there's no restriction whether this can be beyond 1 or below 0. And it's not clear how to interpret that, right? Because Y is probability. It's no meaning of probably more than 1 or probably less than 0, okay? But anyway, you still can say more than 1 is very likely, less than 0 is very unlikely, but you can do that. But some people some experts suggest no matter what, use LPM is the easiest because the interpretation is easy. Okay, so people would recommend that compared to the next 2 model I mentioned. So this is some further interpretation I'm not going to talk about. I will focus on the new thing, about profit and logic. Okay, and one drawback, as I said, is it can go beyond 1 and go below 0. Okay, and how do we avoid that? Is we call the profit model or logic model. Okay, if you learn any other class, it's always like this too. I mean, there are more, but this 2 is the most common one. You can fit many things, but this is the most common one. And how do we do that? Okay, of course, you don't worry about this. I show it here just to show what it is. Okay, by itself, you notice I just change one sentence in the code, then you're done. Okay, in the Python code. So what does that mean here? So now look at the equation here. Okay, remember for linear regression, what we have is this, right? Beta 0, beta 1x1, so on and so forth, right? There should be plus here. Okay, and the probability change according linearly is a linear function, right? In the linear regression. Now it's non-linear, some transformation. Okay, the transformation is like this: e to the power 1 plus e to the power. Okay, EXP is exponential, it's 2.713 raised to the power. Okay, and why is the case? Because this thing, if this crazy guy, I don't know why that comma there. I think I shouldn't copy from the publisher website solution. I should write my own for this one. So you notice if this guy is very big, EX exponential to this guy is very big, this is close to 1, right? Is that clear? The EXP guy is very big, is 1. If EXP guy is go to 0, close to 0, then it will be that. Just to remind you what is this, okay? For many thousands, they will know what do I mean by that, but EX is like this. Right, this is 0, right? If you remember the math, right? When this is function of E of X, right? If X is very large, then it's positive. When X is 0, it's 1 and it's negative, right? So regardless of what actually go from 0 to 1, right? And this is called the logic model. And if you remember, this is the logistic distribution we learned in the topic 2, okay? Lesson 2, we cover that, okay? And this is the function, right? We just do that, okay? Instead of linear. And this logic. The other way around is to model this as a normal, okay? The CDF of normal, okay? And if you do that, that's called profit. Okay, if you don't get it, let's come to here. Let's draw a diagram. How do we fit this guy in? The following. So I hope everyone would be comfortable with the normal bell, right? Everyone would be comfortable with that. But this is the F, right? This is mean mu, right? This is what you learn, right? I hope at this master class, you shouldn't have issue with that one, right? And F, you can change to big F, right? The CDF, right? The CDF will be something like this, right? If you learn, it's something like this, right? Go to 1 here, right? This is 0, right? The CDF, right? Come from infinity and go to the mu will be go up, right? But this is just integration, right? Keep integrating, right? It's just this graph. So what the, okay, and this F function is a CDF is what the S function is what this said. This is CDF function for normal. Okay, but of course they look at the standardized normal, right? Which is normal with mean 0, sigma 1. That's it. Is that clear? Okay. And of course, probably you will not even care what it is, right? Just a model to fit. That's it, right? That is something you need to remember. I'm not expecting you to remember any of this, but you need to know probably in your head there's some way to fit it, and they're different. And that's 2 things. One is called logic, one is called probit. That's it. Okay. And logic means logistic function. Probit means normal. I think that's the best you need to remember if you ever want to remember. Okay. And look at the only difference in the Python code is this only. This is the only difference. If you remember the code we did for ORS, we just say ORS. The only difference, we just say probit or logic. Is that clear? That's very simple, right? There's nothing deep here in terms of code, right? I have the data, right? I have 2 x1, x2, right? And I have 0, 1, 0, 1. I just add a constant, fit the model, and that's what I have. Is that clear? So it's extremely simple, right? ORS is ORS. I probably say probit. That's it. Okay, and probably the important part is not the code, right? Because you can just, because the only difference when you just apply in your model, you just change your X or X, Y, and it's just copy the code, right? It's very simple to implement this, right? Because there's nothing programming here, right? If you really think about this, when you actually work, when just change the X and Y and you're done, right? So, but the only important part is how you can interpret this guy, right? Because it's the only thing I care, or you should care. This, okay? And you can say logic regression, okay? And the method's called MLE. I'll explain at the end of a technical slide. I'll explain how we get the coefficient, right? Because remember, the coefficient is still we still want to get the beta, right? And I don't tell you how the beta comes out, but we'll do it soon, okay? I'll tell you what do you mean by the beta, okay? And you will see that bunch of coefficient and bunch of p-value, okay? So this p-value is more than 0.05, so rubbish model. So you can just throw away, throw to the bin. But anyway, because of I create a model, data is just so rubbish, so that's why it's rubbish, okay? So this confidence will be like this as well, okay? And later you will see there are two things called pseudo R square, okay? Pseudo means fake. Fake R square is something is like a fit like R square, but not R square. Okay, so it's somewhat like R square, which means that the bigger the better. Okay, that's it. That's the thing we need to know. We don't need to go anything further. And not likelihood, we'll talk about that very soon. Okay, but these are the measures that you would care about the fit. Okay, and the easiest way to look at the R square, pseudo R square, is actually like R square. Okay, but you have to fit this into this context. Okay, so but in your head, you just think about R square, the same thing. Okay. And logic, okay. One of the problem of logic is nonlinear, right? You remember when we talk about a nonlinear model, if you still hopefully still remember, is you have y equal to beta 0, beta 1x, and beta 2x squared, right? For this one, if you, sorry for, I have some calculus here. If you don't know calculus, then it should be fine. But anyway, if you try to see this, right, it's nonlinear. Suppose beta 1, beta 2 positive, something like this, right? If they're positive. So it means that the slope, right, x and y is depend on the location of the x, right? If you don't know calculus, that is what it means, right? So it really, the slope is the slope. It depends on where x is, right? Because this graph is nonlinear. It's not constant. If the linear is always the same, okay? The same goes on here because it's nonlinear, right? So it depends on where the location, when you look at the marginal effect, right? When I say what happens if you change x a little bit, how does the y change, right? Right? You compare two different value of x, right? Compare to different y. Then what we do in probability logic, you call marginal effect, is use this function, the marginal effect at mean. So it has many value, right? But you calculate the value of mean. Okay, so in the context of the quadratic, right? Here we will calculate depend on x, but we calculate the value of mean of x. That is what that means. Is that clear? Because look at this quadratic. The slope depends on where you are, right? And the case you calculate mean means I look at x bar, look at this slope. Okay, and logic the same idea. Okay, you can take a differentiation of that guy if you really want to do it. I mean, if you are doesn't, then you know how to do that. But you just take a differentiation on that guy, respect to x1 if you want, and then you evaluate everything at the mean. That's the same thing. Okay, I don't think you care the logic, but why you care about that? Because that is the regression, right? Look at how x1 changed. Say x1 changed to the lead to how many change in y1, right? Loosely speaking. Okay. So how they're related, right? In some sense. Okay. And if you do this marginal effect, you print that out. Can I get bigger? I can't get bigger. But this is very similar to the coefficient when we look at the regression. Okay, you look at this number. Of course, this is not significant, but this is the thing that you would use to compare with the ORS, the PL, or the probability linear model, linear probability model, LPM. Okay, let's see the example. You will probably get what I'm saying. This is profit, just change the profit. So all the things remain the same. So you can see this same outcome, very similar, not significant. Okay. So maybe this example. Okay. So if you try to run probably and logic looks actually very similar, not much different. And probably you ask why people do logic or profit in the old days, because profit is more difficult to calculate because normal is not closed form solution. But logic, you can derive some property. So that's why logic is older technology and profit is newer technology. But anyway, you have computer, so doesn't really make a difference anyway. Okay, so let me show you the result. Okay, this one is looking at the very similar to y hat y plot, right? And probably it's not very good, but I mean this is the best one. Look at this is the table that you would be expected to do. Okay, and I have a table. This is LPM, is the linear probability model, right? Remember this: smoking make you 6% less healthy, and exercise regular make you 5% more, right? And you run a logic of profit, they're coefficient, right? But coefficient by, sorry, you don't get this one. Coefficient just coefficient just simply means that I run this probit. Coefficient means just the what is the beta here. Oh, what should be the number here? It has no particular meaning. Yes, so that's why you look at the marginal. Yes. So that is, so how you use this table, okay, that's a very good question. Usually we will have a coefficient here, and we have that guy. This column 2 is not very useful, except looking at the sign, looking at how whether the positive or negative, and that's it. And you look at the column 3. Column 3 is the thing you use. So that's why sometimes we just show you the column 3. They show it column 2 because they show you actually the same thing. Because if column 2 is have a 2 star, column 3 is the same thing. So that's why for our purpose, actually for our class, you would compare 135 is the thing we care. Okay. This is valid mean, and you can see there is not too much difference, except say, well, logic whether female or male has some difference, right? But this makes sense because usually in all the data you observe in the real world, women live longer. Okay, I don't know why, but that's the data tells you. Usually women live 1 or 2 years longer, at least. And here, these are the data, right? You don't see too much difference there, right? No matter you do probit or logic or linear, it's very similar. Okay, so that's why usually, yes, your question. So that's why if they're so similar, usually we're happy just do LPM. Why? Because it's easy to explain, right? Because it's linear, and turn out that it's very similar anyway, so you don't really bother. But that being said, probability logic do have reason you to use it because you're at the mean, right? Value of X. What happened for prediction model? You care thing is not at the mean, right? You the value that is away from mean, then how you do the prediction? For prediction or estimation wise, these are better, right? And although I didn't put it there, but you don't have to, if you know Python, right? You notice I only do the mean, right? But actually you can do it any other value if you want. You just put the vector there. Put the vector X, then you just predict at anywhere you want, right? So that means that you can see, right, when this is near the mean, that is linear is very similar, right? Very similar. But away from the mean is, look at extreme value, more far away from the mean, then probability logic is better, right? But I hope I answered I have answered the reason why you want to look at that. Okay. So now try to give you how you say how good the fit is. R square is not good, as we have said, right? Because it's non-linear. So R square doesn't mean anything in that context. So we'll use the pseudo R square. Okay. We don't explain what it is, but you often see any software give you this one. So of course, same as R square, higher the better. That's it. Nothing to say more. The second one is, as I said, this guy, right? This is if you try to put y hat and y, just how high is that guy, right? How the sum of square error, similar to sum of square error, right? Same sum of square error idea. And there's a log loss. This is something that we don't cover. I just put it here because we're not really using that for a purpose. Okay. And I don't think I need to go detail, but because this is same as ORS, right? And this is your predicted y, right? And then you just look at each value minus the y hat, and this is square for each term, and some mean of that, right? Or some of them is fine, right? But in this model is the mean because this is the MSE, right? This is look very similar to the MSE idea, right? But we don't call it MSE because it's different, right? Slightly different from that. Okay. So here, what they try to show you is there are three models, which model to pick, and turn out to be these are very similar, R square or the score or that loss. So that's why it doesn't really matter. Usually that is like this. You don't actually can tell which one is better. And then we're so similar that we don't want to pick anyone when anyone would work. And as I said, if you want to do your model or data near the mean of your data set, then make no difference. If your prediction or your model is going to be extrapolate or interpolate somewhere far away from mean, then I think you should do logic appropriate. Okay. In terms of interpretation, the linear probability model will be fine. But you just want to say more or less, right? Look at the sign. But if you want to quantify things, then probability logic is the way to go. Okay. And because everyone uses probability logic anyway. Okay. LPM is good for you to usually you would do it as a first round exercise to see whether your model makes sense. And from that on, use probability logic because that would be appropriate model and maybe people will use it. But that being said, I mean, this free model, either one you use, no one will complain because this is very standard. Okay. And this is the y hat y pot, as I mentioned. I'm not going to talk about this because I don't think it's I don't use it in my work, So that's why I don't think it's very important. If you want, you can check out those. What I want is spend my time talk about this. Okay. And this is, if you learn it, it will be very powerful tools. So you learn the regression method is minimize the vertical distance. Right, if you still recall, right? I just draw it here. I draw it here, right? So how we do estimation? If you remember, our regressions like this, right? The scatter plot, right? This is X and Y. How we're going to do is try to find out, well, different lines, right? Try to figure out different line, the many possible line. And we look at, by having different lines, and actually we have different beta 0 and beta, sorry, I use the notation we have is different alpha, different beta, right? And alpha is the intercept and beta slope, right? By rotating or shifting, you look at the vertical sum of the square distance. That's how you fit this kind of model, right? And this model has nothing related to statistics, right? Just exercise, just algorithm, right? There's no distribution of probability inside it, right? Is that okay? So, but some of you, if you learn regression in the undergrad, there's another way to match it. It's called the maximum likelihood estimate, MLE. Okay? How MLE fit in this framework is the following. You would remember the model. Let me write that down. The model we have is just simple regression. Alpha plus beta X plus epsilon, right? This is a probability model, right? For some X, you have a constant alpha plus beta and epsilon, right? And epsilon, if you assume a bell, right, means 0, right? And for some sigma square, okay? This is not 0, that's not 1, right? This is sigma square. Okay? So, and you can think by MLE, which means the following, right? I imagine in the world that I observe some X. I have some X here, right? Where's my pen? I have some X here, okay? And according to this model, I will have, I don't know, alpha plus beta X, right? Here. And I have some normal here, right? So it can be somewhere like there. The data can be somewhere here, right? And many data here, right? Right? And turnout depends on scenario, things we realize. Okay? So, and what is maximum likelihood? Is look at this model. You have 3 parameters here. Okay? First parameter is this guy, alpha. You have beta, you have sigma square. Right? And remember your scatter plot, right? Okay. And what we are doing is looking at this, right? Can be written as an epsilon, right? And if this follow normal, right? By drawing different epsilon, right? It can be depend on how it realized on the bell, right? So suppose I change this sigma, right? Suppose this is epsilon, right? I fix alpha and beta. Suppose this case. I know alpha and beta. I just do the simple case. I know alpha and beta. Okay. alpha and beta is well known. We know this is what we need to find is this sigma square. Okay, and if I know what is alpha and beta, what is left is I try to figure out different sigma square, right, to fit this line. If this is a sigma square is compare the black one to the green one, okay, and we want to see which one would fit better. Okay, let me repeat the statement. Okay, what we're doing is the MLE is looking at, try to look at this parameter. Okay, there's a distribution here to fit. Okay, if you suppose the easiest case is I know alpha and beta, suppose, then what is left unknown is this sigma square, right? I fit alpha beta, then depending on data, I will have a bunch of error term, right? Then I try to vary my sigma, okay, such that this thing is the best fit, right? But of course, in the viewer, I allow my alpha beta to change. Okay, the MLE is the idea is that I would try to adjust my alpha and beta and sigma such that it's the best fit. Okay, and the fit is called likelihood. So that's why it's called maximum likelihood estimate. Okay, I don't want to go to technical part, but that's what it means. You calculate, given the data, how likely you achieve this, and then you just maximize. Okay, the idea is no different from here, right? If you remember the regression, okay, if I fix the slope intercept, I can have for each point, I can have the measure of the epsilon. I can plot a residual plot, okay, and then by changing this sigma, I can find the best fit sigma. Okay, but also I can also change alpha and beta, okay, so that this is the best fit. Because by changing alpha and beta, this red dot will be different, right? Because it depends on how you draw this thing, right? This thing will be different. Then I want to figure out the best alpha, beta, and sigma to fit this one. And that is, and if you run the regression, I didn't talk about that, but if you assume this is a normal, okay, the coefficient you estimate in this way, same as what we think about the minimize the vertical distance square. So let me repeat. If you look at the regression we teach you minimize the vertical distance square. It will be same as you assume the error follow normal distribution. You try to figure out what's alpha, beta, and sigma to best fit the model. The same thing. Of course, if you assume it's not normal, then what you get is different from the standard minimized vertical distance. Okay, if you assume it's uniform, you assume certain kind of crazy type, is not the same. But if you assume it's normal, then the same. Okay, so same here is I would look at different beta, okay, to fit the data such that this is what we call likelihood to realize most, right? Because assuming the model is correct, right? And then we have different x, right? By changing different beta, I know how likely this appear or not, right? Because it's only 1, 0, right? I can explicitly write the probability, right? If 1, then this realized, 0 is not the realized. Okay. So this is the idea. Okay? Of course, for those of you who never learned MLE, it will be very tough. But the main thing you need to remember is the following. MLE is used for the case where you would assume the data, you have to assume the data follows certain kind of distribution. That has to be parametric. Okay, parametric means that the distribution can be described by several numbers, right? Normal, described by mean and variance, right? Exponential is just a one parameter. Poisson also one parameter. Binomial is N and P, right? There's some parameter to fit. And MLE is trying to say, okay, given the data is here, okay, I try to change my parameter such that the realization of this or likelihood is the highest. Is that clear? Say, suppose the regression case, right? Is the idea is, okay, suppose this is the, I just a line. Suppose I try to fit the bell curve everywhere. I try to make sure that the way I fit this line and I try to fit this sigma is going to be the same everywhere. So the highest cases, right? If I try to make the beta very big, then I'm not going to fit, right? If I try to make the alpha very high, then I'm not going to fit, right? I try to adjust this two and adjust the sigma such that this is the best fit. I hope it's okay, but I'm pretty sure that's difficult because when I learned this, I mean, undergrad, I spent several weeks to understand what's going on there. So it can be difficult, but it's technical. So if you don't know, it's fine. We're not going to ask you for that. Okay, and but that explains why I want to talk about this, because the book talk about that, and you will see why when you run the regression logic here, we have what we call log likelihood here, this entry, and you want this entry as big as possible because you maximize that guy. Okay, and why log? The reason is when doing maximization, you maximize something, or as long as they're positive, same as you maximize the log of that. Okay, I mean, I don't want to go. Okay, that the idea is like this. Since some of you have not happy with what I'm saying, so you maximize L1 dot L2 dot Ln, okay, is equivalent to maximize log of L1 plus log of L2 log of Ln, the same thing. Okay, by maybe choosing some parameter here, ABC, the same thing. Okay, this is standard result from mathematics, but that's why log likelihood. But you can just say, I mean, the same thing. Okay, but anyway, I know it's something tough for you to understand. That let me summarize before I break is, if you, the simplest thing you can remember, you need to remember is when you have y is 0, 1, you don't use OLS. You just use profit or logic, and that's done. Okay, and to interpret your result, usually use the marginal effect in the mean. Okay, and turn out this is very similar to the OLS. And the reason you want to do this is because if not at the mean, they're different. And when you run the model, that's what you need, right? Because you want to say away from the mean how you use the model, right? So that is the thing you need to know, and that's it. Okay. So after the break, we talk about time series. I'm sure some of you have problems during the break, so let's have a break, and now I'll try to answer them. So time flies when it's a break always. There's always not enough time for break. It's very natural. I mean, I could have a break until the end of the day. Right? There's no problem for me, but then you don't learn anything. So that's not good. So but don't worry. This one is something I think is very simple. Because we just teach you one or two techniques that how to handle this problem. We don't even go very advanced, so it's very simple technique how to handle this. So time series model usually is very useful in macro or financial data, and of course your IT manager that is also very important because you have observation for individual over many times. Because look at, say, if your manager look at the user using TikTok or Little Red Book, right? They keep, is it right? So Little Red Book, then I don't know, my wife really like Little Red Book, but I never found it any interesting anyway. But you would just keep scrolling, right? And what they show you, right, is depending on what you have read, right? If you keep reading gossip, then keep reading gossip, right? If you want to read some CP stuff, then they will keep showing you CP stuff, right? Right, that's the thing. So, so time series. Oh, there's a paper talk about CP thing. Anyway, not. Time series regression. Is basically, as I said, you have observation of one guy over a period of time, many period of time. Okay, and this T usually very large. Okay, and as a IT manager, you often have this kind of model, all kind of data, right? Look at your phone, you keep scrolling, then you always have the same thing, right? And then how much time you spend on this video, and so on and so forth, right? So there's some terminology here, very simple one. If you learn time series, there's nothing new there. The first terminology is called frequency, is how frequent you get the data, right? And if you're IT manager, basically you get every single second you have the data, so it's easy, right? And IT manager also, you would care about, if you manage a server, right? Then they say how many traffic comes in. They're all time series model, right? Even you don't do a user, you look at from a server perspective. And one first very important operation on a time series is called the first difference. Later you will see this is probably the single most important thing we learn in this class. For time series is looking at, take a difference between the today's value minus the last period value. Okay, and this to be turned out to be very important. Okay, and this delta y will characterize what we call the trend. Okay, and the trend can positive is if this guy first difference is positive, negative is negative, right? It's go up or go down, right? And if linear or exponential, so maybe I draw a graph, maybe easier to understand because it should be very slippery right now for many of you, right? If this, right, that means delta y positive, okay? And this is delta y is negative, right? And this, right, is delta y. If delta y, this is fine. If like this, right, delta y is a constant, right? Right, same as here, right? And for green one, it's exponential, right? So that is the idea, right? And often data will often exhibit this kind of trend, okay? And why this is important? Because if there's a trend, we don't know how to handle it, okay? So we take away from the trend and understand what is not the trend. So that's why people in time series call detrend the data. Okay, take the trend away. Okay, you probably look at economics, right? Look at the GDP or unemployment or whatever. They look at detrend data, right? They remove the seasonal effect, right? Because say people in the Chinese New Year or the Labor Day or the national holiday, right? People tend to spend more, right? Tend to go around more. So you have to comparison, you need to detrend it, right? As IT manager, you look at the website data or well, you look at the times data, then you have to detrend the data. At night, people are different, right? At midnight is also very different, right? During the day is also very different. So you have to make sure the data is properly detrended. Their overall time trend, also seasonal trend, or the hourly trend, right? Or even look at, say, simple look at the restaurant, right? Look at data, how many customers come in, right? You know, to as a model, you have to the time series data you have to look at, okay? During the lunchtime, there's a bit pretty different from the tea time and the dinner time and the breakfast time and the night time, right? Different time period are different. So you have to understand what's going on. You have to take away those things. Usually what we do is do the dummy variable, control the time. But anyway, later you will see. It's not complicated. It's basically what we do is just like this normal regression, but we add something there. Just like the property logic. We add some different tools that will everything be similar. Okay. And the first thing, the next thing we learn the time series is called stationarity. Okay. And why is important? Stationarity simply means that regardless of the time, okay, the underlying uncertainty or the distribution, as you can see here, actually is the same. Okay. The reason why we need this is if this doesn't hold, then there's no point doing data. Okay. And why is the case? Consider the case you look at a lot of TV shows, right? And the girl said, "You change. Okay, you don't behave. You don't love me anymore. Okay, you no longer with me. You don't want to talk to me. You don't reply my SMS, my message within 3 seconds. Okay, and so on and so forth. Okay, and you see the behavior is very different, right? And if the guy has changed, right? So things are different. We can do analysis, right? If the guy is keep changing, right? And you compare behavior, there's no point to do anything, right? So same idea here, right? If the underlying mechanism generate data, what's called data generating process, is keep different over time. So there's no point of doing analysis at all because the data actually don't tell anything, right? You can imagine if you have a perfect model to know what's going on in your website, right? Suppose your website has changed, right? Suppose your website before you were selling noodle, okay? And today you change, you don't sell any noodle, you sell la tiao, okay? Then the data in the past has there's no use, right? Okay, so that is the idea, right? You have to make sure that the data is the underlying is not changing, okay? And if underlying thing is a trend over there, you have to look at the trend, right? So that's why it's detrending, but later you will see, okay? And the next idea is called serial correlation. Serial correlation is a basic idea in time series, and the basic measurement is the observation across yesterday. Is it going to look at the correlation, how they're related, okay? And say for stock market, okay, or many sales data, usually it's positive, right? The more you sell today, you're going to sell more tomorrow, right? The price is high today, is high tomorrow, right? And but sometimes negative, but most of the case, most of the model are positive, okay? And this is usually you want to use it to help you to do better estimation, okay? So this data usually you would look at what we call I didn't put it there, but usually even the book doesn't tell you, but this process it's not required for a class, but usually this is called AR1. It's auto-regressive of degree 1 if you learn time series. Is what it said is the value of today depend partially on the past, and that is something new today. Okay, that is AR1 indeed. If you ask me, I mean, we don't cover it, but people would say AR1, AR2 is already the model that you need for time series. It will satisfy for 90% of the model. But that's the model, AR model. But we are not learning AMA model, but this is usually the model that usually you would think would fit most of many of the situation. Okay. And the particular case of the AR1 model, or this kind of style model, is what we call the random walk. I hope everyone would have at least heard of that. Right? Random walk is what? It's a guy like me. If I drink enough alcohol, right, then I don't know where I am, right? I just walking, right? Then I can't walk straight line, right? I will walk left and right, randomly. That is the random walk. Okay, what it said is where I am is same as what I was, right? But there's a random thing in my head. It's just like I will fall here, I fall there, right? So that is the random walk. And random walk is something that you can't estimate, right? And that is the model. Okay. What is random walk with drift is you can imagine that if I am on the railway, although I mean I'm on the train. Okay, the train is moving, right? And I am drunk, right? I am moving and drunking, right? Okay, I basically just like the following. The random walk is usually like this. Okay, and with drift it's like this. Okay, so that's the drift. Okay, and they actually some of you may have heard one thing is called Brandian motion. Okay, and this is related to the random walk. Okay, and we're not going to talk about that, but that is closely related to the random walk idea. Okay, I wonder with trend drift the same idea. Okay, and this is the random walk. Okay, looks funny, but one thing I want to say is if your data is actually random walk, then you can go home. Why? Because no way to predict that you're done. Very happy. Okay, so actually if you learn finance, that's what actually in the 70s and 80s they think the stock market is random walk. Okay? Then actually turn out to be like this. I mean, if you understand the finance and then you look at random walk, actually a lot of things looks like a trend actually as a result of random walk. And many people believe that is the stock market is random walk. Okay, so you can go home. Okay, not surprising because look at the stock market is like crazy. Okay, all the time. So random walk is actually not jokingly. A lot of people think if market is efficient, what you observe the price data is a random walk, right? Because the current price is absorbing all the information. There's no more trend. So what is moving the stock price is just news, and news is you don't know, it's random. So random walk is a good thing. And indeed, you look at foreign exchange market, random walk can be a good thing because if so many people are trading, random walk actually is a good one. But anyway, I'm not going to talk about economics. It's too far away from the ITM. And here I want to talk about one thing, because as I said, if it's a random walk, you can go home, right? That means that you need to see whether it's a random walk. I'm not going to talk about detail, but I want to mention one thing that would be stick into your mind. It's called the Peter-Piron test. It's to test, it's called the unit rod test. It's test whether there's a random walk, and that's it. I'm not going to talk about it anymore. That's it. Because to talk about that is a PhD level. So that's it. And probably you want to ask, how do you do that? Okay. I'm not going to talk about detail, but that is called, we can call the Dickey-Fuller ADF test. There is something we can do, but I don't think you ever need it anyway, because you are not a macroeconomist. You're looking at stock price, and for your all data, you don't need to worry about that. Okay. But if you want to check, you can check it. Okay. But usually, unless you're working on financial data, I don't think this matters to you. Okay. I put it here is because of the textbook has. And for ITM, I don't think you would have any chance to need it anyway. Okay. So you don't have to worry about that. Unless you believe it's a random walk. Okay. So the question is, suppose you're unlucky, you think you got a random walk, what are you going to do? Very simple, don't worry. If you're a random walk, you just do the first difference. And then you're done. Then you will not be random walk. If still a random walk, you do the first difference again. And then do the regression. Okay, let me repeat the statement. Okay, if you look at data, it's a random walk, but usually you don't. I mean, suppose you have. Okay, and then you also run the regression, then you can run the regression will be wrong. Okay, right? You try to. What I said is, suppose you want to run the regression, right? Y is equal to bunch of X, right? Say beta 1, beta 2, right? And if your Y is actually a random walk, which I said is unlikely to happen, but if happen to be the case, what we're going to do is, instead of looking at the Y, you take a difference. Look at the rate of change. Okay? And if this change is still random walk, do it again until you no longer random walk. That's it. That is the solution to that. I mean, you learn times that's how they teach you. Okay? And you just first difference until it's no longer random walk. Okay, that's the done. But as I said, you never, I would doubt you would ever have a chance to deal with the random walk, because you handle the human data, you handle this random walk is, you never have that chance to have that. So I don't think you have to worry about that. Okay, but in the case where you happen to be, then you do the random walk. But usually, I doubt any of you would ever come back to this one. But rather, I think the seasonal variation is thing you would be needing for your actual practice. Because as I said, look at the website data over time, and it's not uniform. So you need to control the time dummy. That is the thing you need to remember. I think it's more useful, right? So suppose the website data or the consumption data, you have to control the year, day of the week, and hour of the day. These are the things that you need to control. Okay, this is, I think, is more relevant for analysis. Okay, and to look at the stock price data as an example. Okay, and you can see the stock price look like this. Okay, and this is, I mean, without looking at this crazy number, you think this is a stable. But if you think there's a trend here, you have to take away the trend. Okay, detrended, but this is the index value. Okay, and what they do is they do the Peter-Piron test. Okay, and they figure out that it's non-stationary. As I said, only stock price would have this issue. For your case, you don't have this problem. And if that's the truth, then you just, what they do is do the look at the rate of the return. Right? Take today over this date, and then over the mean, or you can just take the log. Okay, you can do some transformation until it works out. Okay, and you can take a difference, take the relative difference, take whatever thing you like until it becomes stabilized, and then you do analysis. And as an IT manager, I would doubt you have to worry about this, because usually what do analysis is there's some established method already what variable you care. So you just run those regression. So I don't think it's matter to you for this one, but I keep it there because the book, otherwise you don't understand what's going on. And this is the return data become very stable, right? You don't have a trend, right? Then this one you can analyze. This is what I mean, okay? You just, if your data is like, there's a trend there, you maybe take log, take the relative difference, so that your data become more stable to work with for the time series data, okay? And this is for index return, the same idea, okay? And now why you can run this regression, if you try to run the Microsoft price and stock price, these two are not stationary, then one regression can be a mistake. So that's why usually you do loss transformation, right? Or you do the presentations, that's what they're doing, right? They log the price for the Microsoft, log the price for the stock market index, and that's how we run the regression. Okay? And probably you ask why he run this regression, right? Is it crazy? Okay? And this regression, if you learn finance, is very common regression. You try to explain the this is actually called beta. If you learn regression, this alpha, right? Alpha investment, right? Beta is a risk if you learn, but otherwise, why they run that? But just try to say, if the beta is high, then it means that the stock is sensitive to the market return. But I'm not going to talk about finance, okay? But just this regression has some reason to be run if you invest in stock market, okay? And the main thing about this regression is you can't just run the price of Microsoft and the S&P 500 because they are non-stationary, okay? We didn't mention explicitly in the regression model. If the model is non-stationary, the regression will be useless, okay? So we have to make sure that it's stationary before one regression to be work, okay? So that's the reason why we mention use time series. This is usually likely to be a problem. Okay? And as we see here, right, there's a time series model. The difference is we have T, right? And if you have trend or random walk, then the regression will be wrong. So, but as I said, for ITM application, you don't have this issue. Okay. The main thing is for you is to look at the second and third bullet point, seasonality and zero correlation. Okay. That make your regression less valid, or you have to adjust it. Okay. Seasonality later you see just add dummy. It's very simple idea. Okay. Let's go to that. It's very simple. That's what it is. Like this dummy. Suppose your monthly data, you just add a dummy, which is if the data is January, is 1. If February, this February is 1. You just run this regression. Okay. Basically, similar to the smoker idea, the CO1 concept, right? If the data is recorded from January, this is 1, otherwise 0. So basically just a bunch of dummy, right? And if trend, you go to first difference, as I said, right? And the next thing is, as I said, the third bullet point there, it's called serial correlation, right? Is because of, I said, people behavior over time are related and it's not captured in the model. Why? Because remember the regression, there's something hidden within right here is we have some epsilon here, right? And what is epsilon? Epsilon is something we don't capture in the model, right? And either we can't observe it or we can measure it. And this thing can be related over time, affecting the guy, right? Maybe this guy is very happy, right? Then he just buy because he's very happy, right? Or he's very sad, then he buy, right? Either he's very happy, very sad, it's emotional impulse buying, or he is very sad, he would do a shopping therapy, right? So that is you can't observe it in your data, right? You look at a phone, they don't show whether happy or not, right? Unless you are some other phone have a spying function. Otherwise, you don't know that guy is happy or not, right? But it's not capturing the data, and that is appear. You will have a correlation in your model, and then the regression with some issue there. Okay, and then what you're going to do is another type of robust standard error. It's very simple. We call the Newey West estimate as an error. Don't worry, this is very simple. We just estimate regression and just say what is the error type, then you're done. So it's just simply OLS thing. Later you will see. Okay. And the last thing is you run the regression, but also included the Y lag over here. Okay, to control how the past affecting the future, right? Because I said if you try to look at the data, whether you watch this type of video depends on what you have watched in the past, right? So that is how you handle that. Okay, and as you will see, the method is not too complicated. Okay, and I think I am today a little bit over time, but we can talk about it next time. But what I'll talk about next time is to handle this data set. We do use the Panda package, which I will do a little bit more. But you will notice I still want ORS, and I just have the covariance HAC and specify the lag, and then the same thing. Okay, and then you will see the same table goes on. So that's why I often mention you always do this all the time. Okay, but for the time I'll talk about the rest next class, but there's nothing new there. But since I can't finish, so I'm not going to do the quiz next time, so I will just delay after I finish this one. Okay, so enjoy the weekend. I know there's a lot of things I covered today, but we'll do again more. Okay, don't worry about it. We'll do more and more and more, unfortunately. Heteroscedasticity consistent. Huh? Oh.
方差没有，就是这个方差你的方差是偏属于这个偏差的。没讲，但是讲，我没讲，我没看你没有讲，我讲了没讲，都没有讲。你说，人能够回去吗？就是你不叫啊，那个对，也就是。就是随机方式的话，没有办法去 estimate， 因为这后面是断者。就是如果你是断者的话，你还是就是说这个喝醉了，你叫我从哪边的，这样我没有用啊。对啊，所以你确定他不喝醉了，不喝醉的人还是这个，对吧？像我的写，我发现有很多他要求那个可以是那个包括或者是这种。再有，因为开始讲没有那个给你签了，这种然后你要给他你说包括那个就是实践他就对，没有放弃，我先把你的说一遍。Random walk。